Welcome back. In this video, we're going to look at examples of using the binomial series to find Maclaurin series for functions. Let's get to it. All right, so here's our first example. We want to use the binomial series to find the Maclaurin series for this function, f of x is equal to 1 divided by the quantity 1 plus x to the power of 4. All right, and so in order to represent this function as a Maclaurin series, we need to use the binomial series. And the binomial series is the Maclaurin series that represents the function 1 plus x quantity to the power of k, where k is any real number. All right, and so the binomial series looks like this. We have the sum from n equals 0 to infinity of that value of k times the quantity k minus 1, then we would multiply by k minus 2, k minus 3, and so on until we get to k minus n plus 1. Another way to look at that is we have k minus n minus 1, you're going to keep multiplying by those quantities of k minus some value until you get to the quantity of k minus the value 1 less than the value of n. All right, so that's another way that you could look at it. But then you are dividing all of that by n factorial and multiplying by x to the power of n. And so the first couple terms of the binomial series look like this. For the first term, we just have 1. Then when n equals 1, we have k times x. When n equals 2, we have k times k minus 1 times x squared divided by 2 factorial. When n equals 3, we have k times k minus 1 times k minus 2 times x cubed divided by 3 factorial, and so on. Okay, and so you can see that for this term where n equals 3, that we multiply by k, then k minus 1, then k minus 2, and then we stop because 2 is 1 less than 3. And then when n equals 2, we just have k times k minus 1, because 1 is 1 less than 2. All right, so that's how this part of the series works. If we were to write one more term where n equals 4, we would have k times k minus 1 times k minus 2 times k minus 3, and then x to the 4th power. All right, and that would all be divided by 4 factorial. And so that's what the binomial series and its terms look like. So if we go back to our example, if we want to represent this function as a Maclaurin series using the binomial series, we need to get it in the form of 1 plus x to the power of k. Now we're almost in that form already. We have 1 divided by the quantity 1 plus x to the power of 4. And so what we can do to get it in this form is just move this quantity to the numerator and make that exponent negative. All right, so f of x will be equal to 1 plus x to the power of negative 4. And now our function is in this form that can be represented with the binomial series. In this case, our value of k will be negative 4, right? That is the power of 1 plus x. And so now that we have found our value of k for this function, and it's in the correct form, we can start to write out the terms of the binomial series for that function, and then we can look for a pattern within those terms and represent them as a Maclaurin series. All right, and so if we use these terms that we have here, our function will be equal to 1 plus k times x, and k is negative 4, so we have negative 4 times x. And then for our next term, we'll have k, which is negative 4, times k minus 1, so negative 4 minus 1, times x squared divided by 2 factorial. Then we'll add this to our next term, where we have k, which is negative 4, times k minus 1, so negative 4 minus 1, times k minus 2, so 4 minus 2, and then we have x cubed divided by 3 factorial. Now I'm going to write out one more term here, and that will look like this. We'll have negative 4 times k minus 1, so negative 4 minus 1, then k minus 2, negative 4 minus 2, and then we're going to have k minus 3, so we'll have negative 4 minus 3, and then x to the power of 4 divided by 4 factorial. All right, and we could add more terms from there. And so now we have the first several terms of the binomial series that would represent this function. Now what we want to do is simplify our terms just a little bit, but not all the way, so that we can identify some type of pattern within our terms that we can then use to express the terms as a Maclaurin series. Okay, so if we simplify a little bit, we'll have 1, and then we have plus negative 4x. I'm just going to make that minus 4x, right? Adding negative 4x is the same as subtracting 4x. And then let's add that to our next term. We have negative 4 times negative 4 minus 1, which is negative 5, and that's multiplied by x squared, and that's still divided by 2 factorial. Then for our next term, we have -4 and then -4 minus 1. That's -5, and -4 minus 2 is a -6. So we'll have plus -4 times -5 times -6 times x cubed divided by 3 factorial. And then we'll add that to -4 times -5 times -6 times -7, right? -4 minus 3 is a -7 times x to the power 4 divided by 4 factorial. Okay, now I'm not going to actually multiply these coefficients together. We want to leave them as they are for the most part so that we can identify a pattern in our terms. However, what I am going to pay attention to here is the signs of our terms. So for example, with this term right here, we have -4 and -5. Those two negatives will create a positive value. And so this whole term will just be positive. So we could have 4 times 5 times x squared, and that would be the exact same value. So I'm just going to rewrite that. Those two negatives cancel out. So we have 4 times 5 times x squared. Now for this term, we have 3 negative signs, right? We have -4 times -5 times -6. 2 of those negatives will cancel each other out, and then we'll be left with 1 negative sign, which will make this term negative. So I'm going to erase this plus sign and just bring that negative out front and subtract that whole term, and then rewrite these values to be 4 times 5 times 6. So we'll have 4 times 5 times 6. All right, and that's all multiplied by x cubed. Then for our next term, we have 1, 2, 3, 4 negative signs. So these two will cancel each other out to be positive, and these two will cancel each other out to be positive. So this whole term, where n equals 4, will be positive. So we can just rewrite this to be 4 times 5 times 6 times 7, and that would be the same thing. All right, so I'm just going to remove all those negative signs, and we'll have 4 times 5 times 6 times 7. Okay, and so now you can see that our terms are alternating in sign, right? Our first term is positive, our second term is negative, our third term is positive, then we have a negative term, then a positive term, and that's going to continue on forever. Okay, so that's the first thing that I notice here. I know for a fact that our Maclaurin series is going to involve -1 to the power of n. That's what will cause the terms to be alternating. But other than that, what other pattern can we identify within these terms? Well, it looks like we have some kind of factorial in the numerator of these 3 terms, right? We have 4 times 5, then 4 times 5 times 6, then 4 times 5 times 6 times 7. But it's not quite a factorial because we don't have 1 times 2 times 3 times 4 times 5, and 1 times 2 times 3 times 4 times 5 times 6. Right, in order for this or this or this to be a factorial, we would also need to include those first couple values. And so although they don't represent factorials, we could make them represent factorials by multiplying by a form of 1. And here's what I mean by that. Each of these terms is missing 1, 2, and 3, or technically just 2 and 3, because anything times 1 is just itself. And so what we can do is multiply 2 and 3 into the numerator and denominator of each of these terms. And that's going to allow us to make some cancellation, and then that will reveal a pattern within our terms. All right, so let me show you what I mean. Let me clean up my work. What we're going to have is that this is equal to 1 minus 4x plus 2 times 3 times 4 times 5 times x squared divided by 2 times 3 times 2 factorial. All right, so for this first term, I multiplied 2 and 3 into the numerator and denominator. That does not change the value of that term in any way, right? We're multiplying by a form of 1 of 2 times 3 divided by itself, okay? And we're going to do that for the rest of our terms as well. So I'm going to write out those terms, and then I'm going to explain how that helps us identify a pattern in our terms. For our next term, we'll have minus 2 times 3 times 4 times 5 times 6 times x cubed divided by 2 times 3 times 3 factorial. Then for our next term, we'll have 2 times 3 times 4 times 5 times 6 times 7 times x to the power of 4 divided by 2 times 3 times 4 factorial, and we could add more terms from there. And now what this allows us to do is cancel out this factorial in the denominator, right? So if you look at this term right here, 2 factorial is equal to 1 times 2, and that's just equal to 2, which is what we have right here. So 2 and 2 factorial cancel each other out. Then in this term, we have 3 factorial in the denominator, 3 factorial is equal to 1 times 2 times 3, which we have right here. We have 3 times 2, and then that 1 isn't explicitly written out, but multiplying by 1 doesn't change the value, so we don't really have to have that 1 there. But we would have 1 times 2 times 3 right here, and so 3 factorial is in the numerator and denominator. And then you can see for our last term, we have 4 factorial in the denominator and 4 factorial in the numerator. 4 factorial will be 4 times 3 times 2 times 1. And so those 3 values will cancel out with 4 factorial. And notice that what we're left with in the denominator of every single term is 2 times 3, which is always going to be 6. So what everything simplifies to is this. We'll have 1 minus 4x plus 3 times 4 times 5 times x squared divided by 6 minus 4 times 5 times 6 times x cubed divided by 6, and then plus 5 times 6 times 7 times x to the power of 4 divided by 6. And then we can continue to add more terms from there. And now what we're left with is a pattern that we can identify. In each of these terms, we have 6 in the denominator, and we have 3 constant values being multiplied together in the numerator that we could represent in terms of n. And so let me show you what I mean. If I clean up my work, remember that this first term is when n equals 0, then the next one is when n equals 1, then n equals 2, n equals 3, n equals 4, and so on. Notice how the value of n relates to these 3 constants in the numerator, right? We have n equals 2, and in the numerator, we're multiplying 3 times 4 times 5. 3 is 1 value bigger than 2, 4 is 2 values bigger than 2, and 5 is 3 values bigger than 2. Now, if we look at our next term when n equals 3, we have 4 times 5 times 6. 4 is 1 value greater than 3, 5 is 2 values greater than 3, and 6 is 3 values greater than 3. That same pattern is going to occur for every single term. When n equals 4, we have 5 times 6 times 7. 4 plus 1 is 5, 4 plus 2 is 6, and 4 plus 3 is 7. Okay, and so if we were to represent this as a Maclaurin series, we would represent the numerator with n plus 1 times n plus 2 times n plus 3. Those 3 values are always going to be in the numerator of every single term. All right, and then they're always going to be divided by the value of 6, right? 6 is going to be in every single denominator. All right, now we're almost done with representing these terms as a Maclaurin series. We still need to account for the fact that our terms are alternating between being positive and negative, so let's take care of that. Our first term is positive, and then we have negative, positive, negative, positive. So what we want to add to our series is negative 1 to the power of n, right? When n equals 0, you'll have negative 1 to the power of 0, and anything to the power of 0 is 1, so that will ensure that the first term is positive, and then everything will alternate from there. All right, so that's why we choose negative 1 to the power of n instead of negative 1 to the power of n plus 1 or minus 1. Okay, so now we've taken care of the fact that our terms alternate, but now one more thing we need to add is the fact that each term has x to the power of n, right? When n equals 1, we have x to the power of 1. When n equals 2, we have x squared, n equals 3, x cubed, and so on. So we'll add x to the power of n in that numerator as well. And now we have a Maclaurin series that represents these terms. All right, and if you're ever not sure if it also represents those first 2 terms, I know we really didn't pay too much attention to them when we found the pattern for the rest of our terms. So if you're not sure if that pattern holds for the first 2 terms, feel free to check that out. In this case, when n equals 0, you would have 0 plus 1, so that's just 1. 0 plus 2, that's just 2. 0 plus 3, that would just be 3. So 1 times 2 times 3 would be 6. And so 6 in the numerator and 6 in the denominator, those would cancel out and leave us with x to the power of 0, which would just be 1. And so that leaves us with the value of 1 for n equals 0. And then for n equals 1, we would have 1 plus 1, which is 2, 1 plus 2, which is 3, and 1 plus 3, which is 4. So 2 times 3 is 6, times 4 is 24, and 24 divided by 6 is 4. And so that would give us that 4. And then x to the first power, of course, is x to the first power. All right, so the pattern does hold for all of our terms, including those first 2. So we know for a fact that this Maclaurin series does represent this function. All right, the only other thing that we need to mention is the interval of convergence for this Maclaurin series. And the interval of convergence is going to be based on the value of k for the function that the series represents. And so here's how you can find the interval of convergence based on that value of k. If k is a positive integer, meaning numbers like 1, 2, 3, 4, and so on, right? Whole numbers that are positive, then your interval of convergence will be from negative infinity to infinity. The power series or the Maclaurin series will be convergent for all values of x. But if k is not a positive integer, meaning it would be a negative number, or it would be a positive value that's not an integer, such as 1/2 or 1/3, any value like that, the interval of convergence will at least be from -1 to 1, not including those endpoints. However, if the value of k meets one of these additional requirements, then you could either include +1 or include both endpoints for that interval. All right, so if k is between -1 and 0, for example, -1/3 or -1/2, then your interval of convergence will include +1. But if the value of k is greater than or equal to 0, then you will include both endpoints. And so an example of a value of k that would meet this requirement would be 1/2, because 1/2 is not a positive integer, but it is greater than 0, and so when k equals 1/2, you would have this interval of convergence right here. Okay, so that's how we can find the interval of convergence for a binomial series. And so if we go back to our example, in this case our value of k is -4, and so that is not a positive integer. So we know that our interval of convergence will be from -1 to 1, not including the endpoints, because -4 is not greater than 0, and -4 is not between -1 and 0. All right, so this Maclaurin series that we found for our function represents that function for the values of x between -1 and 1. That is the interval of convergence. Okay, and so this is the Maclaurin series that represents our function that we were able to find by using the binomial series. Okay, and so let's take a look at one more example for this video. Okay, so here's our next example. We want to use the binomial series to find the Maclaurin series for f of x is equal to 1 divided by the square root of 1 minus x. Okay, so remember, in order to represent a function as a Maclaurin series using the binomial series, our function needs to be in the form of 1 plus x to the power of k. And so currently our function doesn't seem to be in that form, but what we can do to change that is first rewrite this square root to be the 1/2 power of 1 minus x. So what we'll have is that this is equal to 1 divided by 1 minus x to the 1/2 power. And then if we move that quantity to the numerator, that exponent will become negative. And so then this will be equal to 1 minus x to the power of -1/2. Okay, so now we're closer to being in the correct form, but remember, we need to have 1 plus x, not 1 minus x. And so there's an easy way to fix that. Instead of having 1 minus x, we can view it like this. We can view it as 1 plus -x to the power of -1/2. All right, so we still have 1 plus x, but x will be -x. So when we write out the terms of our binomial series, we will just replace every x with -x. Okay, so if I clean up my work, this right here is what our function is equal to. So f of x is equal to 1 plus the -x to the power of -1/2. And so this is in the form of 1 plus x to the power of k, which means that k is equal to -1/2. Now, based on those rules we were looking at earlier, we can already see what the interval of convergence will be for our resulting Maclaurin series, because the interval of convergence is based on the value of k. In this case, k is -1/2, so that is not a positive integer, so the series will not be convergent for all values of x. But what is true about k is that k is less than 0, but greater than -1. Right? -1/2 is between -1 and 0, and so because of that, our resulting series will be convergent on the interval from -1 to 1, including +1. Or at least that's what it would be if our function was in this exact form, but it's not. So our interval of convergence is actually going to look a little bit different than this right here. We have the correct starting point, but this is the interval of convergence if we have 1 plus x to the power of k, but we have 1 plus -x to some power k, right? And so what this interval of convergence is saying for this function is that when x is less than or equal to 1 but greater than -1, that the Maclaurin series for that function will be convergent. However, in this case, we don't have x in our function, we have -x. So to get our interval of convergence, we will need to replace this x with -x and then solve for x again and see how our interval of convergence will change. All right, so what we have is -x less than or equal to 1 greater than -1. And so now what we want to do is solve for x by dividing each part of this inequality by -1. Now remember, dividing by a negative value with inequalities flips the inequality signs. So what's going to happen is we're going to divide each part by -1. So we're going to have 1, x, and -1, right? -1 divided by -1 is +1. -x divided by -1 is just x. And 1 divided by -1 is -1. But we're not going to have a less than sign and a less than or equal to sign. They're going to flip because we divided by a negative number. So we're going to have greater than and greater than or equal to. And so in this case, x is less than 1, but greater than or equal to -1. And we could write that like this. We would have -1 less than or equal to x less than 1. And so our real interval of convergence is not from -1 to 1, including 1, but from -1 to 1, including -1. All right, so that's going to be our real interval of convergence since we have -x, not just x, in our function. Okay, so let's fix that. In this case, we are not going to include +1, we are going to include -1. So we will have a closed bracket around -1 and an open bracket around +1. All right, and so that will be our interval of convergence for the Maclaurin series that will represent this function by using the binomial series. All right, and so we are kind of working ahead a little bit, but I do find it to be helpful to find that interval of convergence first. Since you find the value of k right away, that way you don't forget to find it later after you form your Maclaurin series. All right, so just keep that in mind going forward. We'll come back to our interval of convergence once we create our series. But now what we want to do is represent this function as a Maclaurin series, and so we need to start by writing out the terms of the binomial series. All right, so remember, the binomial series looks like this. These are the terms that we need to write out. So for this function, our first term will be 1. Then we're going to add k times x, and k is -1/2. And remember, we need to replace every x with -x since we have 1 plus -x in our function. All right, so we're going to have -1/2 times -x. Then for our next term, we'll have plus k, which is -1/2, times k minus 1, so -1/2 minus 1, and then times -x squared, right? X squared will become -x squared. And that is all divided by 2 factorial. Okay, then for our next term, we'll have k, which is -1/2, times k minus 1, so we have -1/2 minus 1, then k minus 2, so -1/2 minus 2, times x cubed, but we're going to have -x cubed divided by 3 factorial. Now I'm going to do one more term, so we'll add this to -1/2 times -1/2 minus 1 times -1/2 minus 2 times -1/2 minus 3, and then we're going to have -x to the power of 4, all divided by 4 factorial. And then of course there would be more terms after that, but I kind of ran out of space to write that there. But just remember that there would be more terms. And so now that we have written out the first couple terms of the binomial series, let's work on simplifying things just a little bit. First thing that we want to do is subtract 1 from -1/2, subtract 2 from -1/2, and subtract 3 from -1/2. We want to simplify all of those values. So if we do that, this will be equal to 1 plus -1/2 times -x. Those negatives will cancel out, so we're just going to have plus 1/2 times x. All right, and then we'll add that to -1/2 times -1/2 minus 1. That's going to be -3/2, right? 1 is the same as 2/2. So -1/2 minus 2/2 will be -3/2. And then we have -x squared. That's just going to be x squared, right? When you square a negative value, it becomes positive. So we just have x squared there. Then we'll divide this by 2 factorial, then add that to negative 1/2 times negative 1/2 minus 1, which is negative 3/2. Then negative 1/2 minus 2 will be negative 5/2, right? 2 is the same as 4/2, so negative 1/2 minus 4/2 will be negative 5/2. And then we have negative x cubed, and when you cube a negative value, it's going to remain negative, so I'm just going to keep that as negative x cubed, and that will be divided by 3 factorial, and then we have plus negative 1/2 times negative 1/2 minus 1, which is negative 3/2. Negative 1/2 minus 2 is negative 5/2. And the negative 1/2 minus 3 will be negative 7/2, right? 3 is the same as 6/2, so negative 1/2 minus 6/2 will be negative 7/2. And then we have negative x to the power of 4. Anytime you take a negative value to an even power, that negative will be canceled out. The value will become positive, so we'll have positive x to the power of 4 divided by 4 factorial, and then there's more terms after that. Okay, and so now we have simplified all of those values, and be careful not to multiply those different values together. We want to keep them in this form so that we can identify a pattern within our terms that we can then use to represent it as a Maclaurin series. Okay, so there's a reason we're not multiplying everything together right away. We want to identify a pattern. We're not worried about what the actual value of the terms would be when we multiply all those little numbers together. Okay, so now the next thing that we want to do here is determine the sign of each of these terms. Let's work with each of our negative signs and see what's going to happen to each term individually. Okay, so in this term right here, we have negative 1/2 and negative 3/2. Those two negatives will cancel each other out, and so this whole term is going to be positive. So we could just rewrite this to be 1/2 times 3/2. We don't need those negative signs, so I'm going to rewrite this here, and we will have 1/2 times 3/2 times x squared. And then for our next term here, we have negative 1/2 times negative 3/2 times negative 5/2 times negative x cubed. And so this time we have 4 negative signs, and those are all going to cancel out, right? These two will cancel out to be positive, and these two will cancel out to be positive, so we're just going to have another positive term. So we can rewrite this entire numerator to be all positive values. So I will do that here. We will have 1/2 times 3/2 times 5/2 times x cubed. Okay, and then for this term, we have negative 1/2, negative 3/2, negative 5/2, and negative 7/2. Once again, we have 4 negative signs. So these two will cancel each other out, and these two will cancel each other out. So this whole term will also end up being positive. So I'm going to rewrite this whole numerator as well. We'll just make all of those values positive, and so we'll just have 1/2 times 3/2 times 5/2 times 7/2 times x to the power of 4. Okay? And so now we have determined the sign of all of our terms. It looks like they're all going to be positive. Our terms are not alternating between being positive and negative this time. And so we don't need to worry about making our power series an alternating series. And now the next thing I want to do is just make these terms a little bit nicer to look at by moving the denominators of these fractions into the denominator of each term. Right, we could pull these fractions out to the front and multiply 1/2 times 3/2 times this whole fraction. And so the numerators would remain in the numerator of the fraction, and the denominators would move to the denominator of the fraction for each of these terms. Okay, so we would keep 1 and 3 in the numerator, and then we'd have 2 2's in this denominator. And notice that that is going to be a similar pattern for the rest of our terms as well. We're going to have 1 times 3 times 5, and then 3 3's in the denominator. And then we have 1 times 3 times 5 times 7, and 4 2's in the denominator. So we can move each of those groupings of 2's to the denominator and have 2 squared, 2 cubed, and 2 to the 4th power. All right, so if I clean up my work, here's what we'll have if we rewrite these terms by moving the denominators of these fractions to the denominator of the whole term. We'll have that this is equal to 1 plus 1/2 times x plus 1 times 3 times x squared divided by 2 squared times 2 factorial. Then we'll have plus 1 times 3 times 5 times x cubed divided by 2 cubed times 3 factorial. And then we'll add this to 1 times 3 times 5 times 7 times x to the power of 4 divided by 2 to the 4th power times 4 factorial. And then we have more terms from there. Okay, so all we did was keep the numerators of those fractions in the numerator of the term and then moved their denominators to the denominator of that term, which just resulted in 2 squared, 2 cubed, and 2 to the power of 4. Okay, and now at this point we're just about ready to start representing these terms with a Maclaurin series. So if I clean up my work again, let's start forming our Maclaurin series. We know that this is going to be equal to the sum from n equals 0 to infinity of some fraction. And so let's start picking out the patterns that we can already see are taking place. Okay, and to help us see what the patterns are, I'm going to label our terms. This first term is when n equals 0. The next term is when n equals 1. Then we have n equals 2, n equals 3, n equals 4, and so on. All right, so notice that for each of these terms, the value of n determines the power of 2 in the denominator, and it determines the value of the factorial, right? When n equals 2, we have 2 squared times 2 factorial in the denominator. When n equals 3, we have 2 cubed times 3 factorial. And when n equals 4, we have 2 to the power of 4 times 4 factorial. Okay, and it actually would also be true for this first term, where n equals 1. We could rewrite this a little bit. Instead of having 1/2 times x, we could express this as 1 times x divided by 2 to the 1st power times 1 factorial, right? This would still be 1/2 times x, because 2 to the 1st power is 2, and 1 factorial is 1, so we have 2 times 1 in the denominator, and so 1/2 times x. Okay, and so we know for a fact that in the denominator of our series, we will have 2 to the power of n times n factorial. That we know for sure. Now that pattern would also be true for the first term where n equals 0 as well, but I'm actually not going to include that in this series. We're going to start this series at n equals 1 and keep that 1 out front, and I'll show you why in a second, but for now, just know that our series is going to start at n equals 1, and we're going to have 1 plus that series. This is how we're going to represent this function. Because once we start to look at the pattern of these coefficients in the numerator, that first term is not going to be included with that pattern, so we're just going to exclude it from the series. Okay, but we'll get to that in a second. Let's work on the next thing that we notice that we have for each of these terms. And the easiest thing to see next is that depending on the value of n, we will have x raised to that power, right? So when n equals 1, we have x to the 1st power. When n equals 2, we have x squared. When n equals 3, we have x cubed. And n equals 4, we have x to the power of 4. So we know we need to include x to the power of n in our series to represent these terms. The only thing that's left to represent now are these coefficients. And the pattern here is not as easy to identify as we would like it to be. Right, if we start with our n equals 1 term, we have 1 as the coefficient. Then for n equals 2, we have 1 times 3. Then for n equals 3, we have 1 times 3 times 5. And then for n equals 4, we have 1 times 3 times 5 times 7. It seems that with each term, we continue to add the next odd number to multiply by the rest of the values. And so in a way, it sort of looks like a factorial, but it's not a factorial because we're skipping numbers. And so we can't express those coefficients as a factorial. Instead, what we want to do is represent it as a continuation of multiplying values where the last value we multiply by will be determined by the value of n. Right, so what I mean by that is we're going to have 1 times 3 times 5 times 7, and then we will continue to multiply until some value that is decided by n. And the way we're going to determine what that last value will be is by looking at the pattern or the sequence of those last values, right? When n equals 1, that last value is just 1 because that's the only coefficient we have. When n equals 2, that last coefficient is 3. When n equals 3, that last coefficient is 5. And when n equals 4, the last coefficient or the last value is 7. Right? Those are the new values that are in the numerator that we're multiplying by with each term. And so as I mentioned earlier, these are just the odd numbers that start at 1, right? We have 1, then 3, then 5, then 7. But how can we express that in terms of n? Well, the easiest way to do that is to recognize that these values form an arithmetic sequence or an arithmetic sequence. Essentially, it's just a sequence where each term increases by the same value. right? If our first term is 1 and we add 2 to it, we get 3. Then we add 2 again, we get 5. And if we add 2 again, we get 7. So we have a sequence of terms that increases by 2 every time. And what we want to do is find a way to represent that sequence of terms in terms of n. And so an arithmetic sequence, we can find a sub n for that sequence by using the following formula. We'll have a sub 1 plus n minus 1 times the common difference. All right, now in this case, a sub 1 is when n equals 1. So a sub 1 is equal to 1. Just like a sub 2 would be equal to 3, a sub 3 is equal to 5, and a sub 4 is equal to 7. We can plug in that value of a sub 1 into our formula. So a sub n is equal to 1 plus n minus 1 times the common difference, which is 2, because each term in the sequence is 2 greater than the previous term. So our common difference is 2, and so now if we solve for a sub n, this will be equal to 1 plus 2n minus 2, right? 2 times n is 2n, 2 times the negative 1 is a negative 2, and then negative 2 and 1 will combine to be negative 1, and so a sub n is equal to 2n minus 1. 2n minus 1 represents what that last value will be that we multiply by in each of these numerators. Okay, so for example, when n equals 2, that last value should be 3. So if we plug 2 in for n, 2 times 2 is 4, minus 1 is 3. When n equals 3, we want to have 5. And if we plug 3 in for n, 2 times 3 is 6, minus 1 is 5. When n equals 4, we want 7. And 4 times 2 minus 1 is 7. All right, and so 2n minus 1 is what we want to write in right here. Okay, so we'll have 2n minus 1. And now what this says right here is that for the terms of our series, we will multiply the odd numbers, 1 times 3 times 5 times 7, up until 2n minus 1. And that is dependent on the value of n. Okay, so that is how we represent those coefficients or those values in the numerator that are being multiplied by x to the power of n. And because of that pattern, this is why we had to separate the first term from the rest of the series. This is why we have 1 plus this series, because if we were to follow this pattern, n equals 0 would have to be negative 1, and that doesn't really match up with what we have here. Okay, our first term is positive 1, so we couldn't have a negative 1 in the numerator of this expression because the denominator would be positive and x to the power of n would be positive. So when n equals 0, we would not get 1 following this pattern. So we had to exclude that first term because plugging in 0 here would result in negative 1, and we don't want that. Okay, so that is why we had to exclude that first term. I hope that makes sense now. It took a while for us to get to that explanation, but now hopefully everything came together and it makes a lot more sense. Okay, and so now we have the Maclaurin series that represents this function. It's 1 plus the sum from n equals 1 to infinity of 1 times 3 times 5 times 7 all the way up till 2n minus 1, and then that's all multiplied by x to the power of n divided by 2 to the power of n times n factorial. And this power series is convergent on the interval from negative 1 to 1, including negative 1, but not positive 1, right? We determined that at the very beginning of this problem. And so that is the final answer for this example. We found the Maclaurin series that represents this function by using the binomial series. All right, and so that is it for this example, and this was the last example for this video. So if you have any questions, feel free to leave those in the comments below. But if you don't have any questions, this is all I had for now, so I will see you next time.